We've talked here and there about how to interpret the derivative, how it represents the rate of change, how it represents the slope of the tangent line, how it represents velocity, but in this section we're really going to take a deep dive into those interpretations and see if we can't really nail down our understanding of the derivative as a rate of change and exactly what it is it tells us in different circumstances. So if we're working with a position function, s equals f of t, the average rate of change of the object over an interval ab is simply given by f of b minus f of a over b minus a. This is not a new formula. We saw this way back in 2.1, and at the end of the day, that's really just the slope formula. But we're thinking about this through the lens of position. So s is a position function. We can interpret this average rate of change in a few different ways. So we can talk about average rate of change, but if s represents a position function, the rate of change of position is velocity. So it can also represent average velocity. And when we look at it graphically, we said it's kind of the slope. So it's just the slope of the secant line, the slope of a line that passes through 2 points. These are all three talking about the same quantity, right? It's talking about this f of b minus f of a over b minus a. They're just slightly different variations of that interpretation. They're just looking through a different lens each time. So whether we're talking about average rate of change, this is probably the most general version to look at here. Average velocity, we're looking through the lens of, well, this is a position function, and slope of the secant line here, we're talking about this graphically. They're all referring back to this guy right here. Now, notice we haven't actually talked about the derivative yet. The instantaneous velocity, right? So it's different than average velocity here. We're saying the instantaneous velocity, the velocity at a given second at a is given by f prime of a, and that this is the slope of the tangent line to f of t at a comma f of a. So remembering that the derivative, the derivative tells us the slope of the tangent line. It also represents instantaneous velocity. It also represents instantaneous rate of change rather than average rate of change. But these two are one is not necessarily better than the other. They both tell us two different things, and we may want to understand both of them. So we're going to practice kind of looking at both here in this first example. So in example 1, I have a figure that shows the position of an airliner on an out and back trip from Seattle to Minneapolis, where s equals f of t is the number of ground miles from Seattle, t hours after takeoff at 6 o'clock a.m. The plane returns to Seattle 8.5 hours later at 2:30 p.m. Part A says calculate the average velocity of the airliner during the first hour and a half of the trip. So when we talk about average velocity, remember we said that was the same as the slope of the secant line, same as average rate of change. So we're thinking about that formula, f of b minus f of a over b minus a here. So I want to look at the first hour and a half of the trip from 0 to 1.5 hours. So average velocity, remember this is really slope of the secant line. So let's actually sketch in the slope of the secant line during the first hour and a half. So we start right here at 0, 0, and I think it would be helpful to list these points. So we have this point right here at 0, 0. And then at an hour and a half, let's estimate right about there. It looks like we have a point at 1.5, comma, what would that be? 600. So we want the slope of the secant line between 0, 0 and 1.5, 600. If I sketched in the secant line, it would look something like this. Even just, I think, this part right here, this is the part we're really interested in. What's the slope of that little line segment? So I'm using essentially this slope formula, and I have everything laid out. I have 0, 0, 1.5, 600. I don't have a function to plug in these x values, but then again, I don't need them because I have the y values already included. So I can say, all right, if I want to look at this f of b, let's call this point b comma f of b, and over here we've got a comma f of a. So let's see, f of b, that'll be 600 minus f of a, well that's just 0, divided by b, which is 1.5, minus a is 0. So I have 600 divided by 1.5, which I believe should be 400, but I want to double check just because I don't trust my mental math. Should be 400, yes. So this would be 400. And then the other thing that I would like to give here, so my average rate of change is 400, but we're talking about velocity here. What are the units of velocity? We have to find our units of position, which are miles per unit of time is hours. So this would be 400 miles per hour. Per hour. So this is my average rate of change over the first hour and a half of the trip. Part B says, now at what times is the velocity 0? So when we talk about just velocity, and I want to draw this distinction between velocity and average velocity. When we talk about velocity, if we don't specifically say, we're talking about instantaneous velocity. So at what times is the instantaneous velocity 0? So if I'm thinking about the instantaneous velocity, what I'm really talking about is where is the derivative f prime of t equal to 0. And this tells us, well, that tells us slope of the tangent line. Where is the slope of the tangent line equal to 0? So if I look at where I have a slope of 0 for my tangent line, if I pick anywhere on the left-hand side of my graph, it looks like my slope is going to be positive, so that's no good. If I pick anywhere on the right-hand side, it looks like my slope is going to be negative. It's this middle part right here that I want, where my graph sort of levels off for a minute. If I were to sketch in the tangent line right here, looks like I would have that flat horizontal line that has a slope of 0. It's neither positive nor negative. So okay, I want this flat part right here. What are those times? Let me erase here just so that we can see a little bit clearer. Looks like it happens between about 3 hours and roughly 5 hours. So at what times is the velocity 0? I would say between t equals 3 and t equals 5 hours. That 2-hour gap. It also says, hey, give a plausible explanation. So talk about why the velocity could be 0. So let's think about this. If the velocity is equal to 0, I want to think about where is my plane going. Well, if my velocity is 0, my plane actually isn't going anywhere. It's stationary. It's staying exactly where it is. So I need to think about, well, why would that be the case? Let's go back and look at our kind of prompt for this problem. It says the following figure shows the position of an airliner on an out and back trip from Seattle to Minneapolis. So we're flying from Seattle to Minneapolis and then back again. So this 2-hour time frame, we might just be at Minneapolis. The pilots may just be taking a break. So the plane is probably just on the ground waiting for passengers to leave and passengers to get back on. So a plausible explanation, I'm not going to write that whole thing out, but you could say something along those lines. They're waiting for passengers to get off of the plane. They're waiting for new passengers to board the plane. They might have crew moving in and out. But the important part here is that when the velocity is 0, the plane's just sitting where it is. So it's just sitting at the Minneapolis airport, not really going anywhere. It's not going forwards, not going backwards. Part C says determine the velocity of the airliner at noon, which is t equals 6, and explain why the velocity is negative. So, okay, I want to estimate the velocity at t equals 6. Let me clean up this graph. At t equals 6, we're looking at this point right here. So if I was to sketch in the slope of the tangent line at that point, see something that looks like this. So determine the velocity of the airliner. I have my tangent line, and I want to look at the slope of this tangent line. Now, if this were a nicer graph, I could just kind of count, rise over run here, but the problem is my y values have a different scale than my x values. So I am going to want to look at probably 2 points, and I'm going to pick 2 points that are roughly on this point. So let's see, I have roughly 5, 1600 right there. And then let's take maybe this point right here. Looks like I've got 7, 800. And if I find the rate of change between these two, essentially I'm just looking at the slope formula. So how about I call this a, f of a, and b, f of b. So let's see, f of b, that'll be 800 minus 1600 divided by 7 minus, we said that x value was 5, right? Yes. So let's see, I will have negative 800 divided by 7 minus 5, that would be 2, gives me negative 400. Again, we're talking about the velocity, so we want to give a unit. This would be negative 400 miles per hour. Oops. Per hour. I keep wanting to write natural log for some reason. Oh my goodness. Per hour. Okay. Explain why the velocity is negative. So this is perhaps kind of an interesting question now. Why is the velocity negative? What does the rate of change represent here? We're talking about the position. So this rate of change describes the position over time, right? The position with relate to time. So if my rate of change is negative, it means that the position, and in particular the miles from Seattle, is decreasing. If I have a negative slope, that value is decreasing. So the number of miles I am from Seattle is decreasing. Well, that means that I'm flying back towards Seattle. That makes sense because it was an out and back trip, right? We flew from Seattle to Minneapolis, and then this is the return trip. So the distance between my plane and Seattle is decreasing. That's why the velocity is negative, because the plane is getting closer to Seattle. In other words, the distance between Seattle and the plane is decreasing. That's why I ended up with a negative rate of change, or a negative velocity here. So this is, I think, just kind of a really nice problem that hopefully illustrates the difference between average velocity and here when we just talk about velocity or instantaneous velocity. Anytime we just say the word velocity without necessarily saying average or instantaneous, we'll assume from now on that we're talking about the instantaneous velocity. We'll go out of our way to talk about average velocity. We'll make sure to throw that word in there if we want to talk specifically about average velocity. But it turns out that instantaneous velocity is a lot more interesting for us to talk about because that gives us slope of the tangent line, which is what we were working so hard to get at the beginning of this chapter. So let's look at one more example, but before we do that, I want to talk about the relationship between position, velocity, speed, and acceleration, because these are all very closely related. If we're working with a position function, s equals f of t, and anytime you see s, you can go ahead and assume that we're working with a position function. If I want the velocity, remember if I just say velocity, I'm talking about instantaneous velocity. If I want the instantaneous velocity, that's given by the slope of the tangent line or the derivative. So if I want to find the velocity function, I just need the derivative of the position function, ds over dt, or f prime of t. Just choose your favorite notation. Velocity and speed are very much related. Speed is simply the magnitude of velocity, which is a fancy way of saying the absolute value of your velocity. So the difference between speed and velocity, speed is just how fast you're going regardless of whether you're moving forwards or backwards. It's just how fast are you going. When we talk about velocity, velocity is speed with direction. So when you have a positive velocity, you're moving forward, you're moving in the positive direction, whatever that may be, whether it's up or whether it's to the right, you're moving in whatever the positive direction is for that problem. If you have a negative velocity, it means you're going backwards, you're moving in the negative direction. But when we talk about speed, we're just saying how fast are you going regardless of your velocity. So velocity can be negative, speed cannot be negative. So it's just the absolute value, again, of velocity. If I want to talk about the acceleration is the rate of change of speed, of velocity. So in other words, acceleration is the rate of change of velocity, so the derivative of velocity. Well, that's just the derivative of the derivative, so it's the second derivative. It's the second derivative of your position function. So d squared s over dt squared, or f double prime of t. So anytime we want to talk about acceleration, we're really going to be using the second derivative of our position function. So let's look at an example here. We're going to explore some of these relationships, see if we can't better understand them. Here I have f of t equals 18t minus 3t squared, where 0 is less than or equal to t is less than or equal to 8. I'm going to start by sketching a rough graph of this position function. And when we say this part right here, 0 is less than or equal to t is less than or equal to 8, this part right here is really just your domain. So I'm going to say, okay, f of t, this is equal to 18t minus 3t squared. This, what do we know about this? Well, it's a quadratic. The leading coefficient is negative. I know the general shape just by looking at it. It's a parabola that opens upside down. So what do we need to say now? We should probably talk about either one of two things. We can either find the vertex or we can find the x-intercepts. I think I would find the x-intercepts right here. So I'm going to take this function, 18t minus 3t squared, and set it equal to 0. So let's see, this factors really nicely. Let's go ahead and do that. I'm going to factor out, 3t. That'll leave me with 6t minus, 6 minus t is equal to 0. Taking each factor, setting it equal to 0, 3t equals 0 gives t equal to 0. 6 minus t equal to 0 gives t equals 6. T equals 6. So that means it crosses the x-axis at 0 and at 6. So at this point, I think we could make a rough sketch, and that's really all I'm going to be looking for here, is I want a rough idea of what this graph looks like. So we really only care about the right-hand side because our domain was just 0 to 8. That's really the set of x values that I care about. And actually, let's do this. We're going to care more about the top part of our graph. So let's look at that. So we want, let's see, 1, 2, 3, 4, 5, 6, 7, 8. We set our graph crosses the x-axis, or the t-axis in this case, at 0. So right here. And at 6, so that would be right here. We also said, hey, this is a parabola which opens downward. So I think at this point we have enough information to make a rough sketch of our graph. You know, it's a parabola that opens downward, so perhaps, oops, let me see if I can draw a pretty good parabola here. I know that if the intercepts are at 0 and 6, it must have a vertex halfway in between at 3 if it's going to be symmetric, so it probably looks, oh, something like this, give or take. Not a perfect parabola, but enough to get the idea of what's happening. So, okay, cool, we have the position function. We're going to come back to this in a little bit. And actually, let me just erase this so that it's not moving into the next problem. Part B says, okay, now find and graph the velocity function. It says, when is the object stationary? When is it moving to the right? And when is it moving to the left? So, okay, let's find the velocity function. We said if we want to find the velocity function, that was just the derivative of our position function. So I'm going to take the derivative of f of t. So that would give me 18 minus 6t. So 18 minus 6t, here is my velocity function. That's the first part. Now I'm going to graph the velocity function. So you can do all sorts of things. I'm really interested in where is the velocity equal to 0? Where is it crossing the t-axis? Because I can look at this, I can see, okay, this is a line. What do I know about this line? There's a positive y-intercept. Again, I don't want to get too lost in the specifics. There's a positive y-intercept. So let's say this is our y-intercept up here. And I have a negative slope. This slope is going downwards. So, okay, the only thing I want to know is where does it cross the x-axis? Does it cross over here? Does it cross over here? Does it cross way over here? Because that is actually going to give us a lot of information. So just like I did earlier, I'm going to find the t-intercept. I'm going to take my function, minus 6t, set it equal to 0, and solve. So 18 equals 6t. It intersects at t equals 3. So that means it's crossing the x-axis, or the t-axis, excuse me, right there. And our velocity function looks something like this. We can't graph it over the, I guess it would just keep going if you really wanted to keep graphing it over 0 to 8, but we're kind of running out of room at that point. So, okay. We've got our velocity function, and hopefully this makes sense. Remember, we said, hey, the vertex, if it's going to be symmetric, has to be halfway between 0 and 6. So the vertex is right here at 3. And hopefully we see, okay, here at the vertex, I'd have a slope of 0 for my tangent line. Well, a slope of 0 of a tangent line means that, hey, my velocity should also be 0. And I see that happening, which is very cool. So, okay. I have my velocity function, and once you have your velocity function graphed, I think it's a lot easier to talk about when is the object stationary, when is it moving to the right, and when is it moving to the left. So let's talk about this. Stationary, and actually let me erase a little bit more even just so that I have some more room. There we go. This object is stationary, so if it's stationary, it's neither moving left nor right. It's not moving anywhere. So the object is stationary whenever the velocity is 0, and that's kind of why I also looked for this point right here. It's stationary at t equals 3. So it's stationary at t equals 3. So, okay, that's cool. When is it moving to the right? This part's a little bit tricky. And I'm going to assume, for the purposes of this problem, we didn't really explicitly state this, but we said we'll go ahead and assume that if we're moving to the right, that's moving in a positive direction, right? If we're moving to the right on our x-axis, that's a positive x direction. So we're moving to the right. We said earlier we're moving to the right whenever velocity is positive. So when is the velocity positive? the velocity is positive on this section of my graph. So okay, let's think about this. Is my velocity positive here at 0? Well, the x-intercept we said was 18. So yeah, the velocity is positive at t equals 0. So I'm going to give this as an interval. So I'm going to say starting at t equals 0. And we said, hey, you know what? The velocity is positive there. So we want to include that number in our set, in our interval. So the way we're going to do that is we're going to use that bracket to show that, hey, 0 is included in the set. We are saying that the velocity is positive at 0. And then when does it stop being positive? So it starts right here. It's positive. It's anywhere it's above the x-axis. So it stops right here at t equals 3. So from 0 to 3. Now, is the velocity positive at 3? No, because we said it was stationary. If it's stationary, it can't also be positive. Stationary means it's stopped. It's not moving. So it can't be stopped and moving to the right. It has to be one or the other. So we're going to say, you know what? This object is moving to the right from 0 to 3, but not including 3. The way we're going to do that is we're going to use parentheses to show that 3 is not included in the set. So there's where it's moving to the right. We can probably determine at this point when the object is moving to the left just using kind of process of elimination. But let's suppose I didn't want to do that. So we said, hey, you know what? It's moving to the right whenever velocity is positive. So I think we can sort of intuit then that if your object is moving to the left, you're talking about where's my velocity negative? Where's the velocity negative? So the velocity is negative. I have my velocity function graphed. That's this red line. Where is it negative? Well, it's negative anywhere below the x-axis. So this section right here, and it would keep going. So where does it start negative? Right here at 3. But again, not including 3 because we said it was stationary at 3. So it begins moving to the left at t equals 3, but not including 3, so we're going to use that parentheses here again. And all the way until, well, it's just going to keep moving to the right forever after that, but we don't want to say to infinity because we have this strict domain up here. So we're going to stop at the rightmost t value, which would be 8. So at 8, and again, we want to know is our object moving to the left at 8, and if I graphed all the way over here, right, I would assume my graph is somewhere down here. It's a negative y value. It's below the x-axis. So yes, absolutely it is. I'm going to use a bracket around that number to show yes, it is moving to the left at t equals 8. 8 is included in our interval. So this gives us kind of everything we need. We could have also looked at this through the lens of making a number line, which is what we'll do oftentimes, but I think looking at the graph really helps. So let me just label these before I forget. The red line, this is V, and the blue parabola, that is S. Part C says determine the velocity and the acceleration of the object at t equals 1. So again, when we say determine the velocity, it doesn't say average velocity, it just says velocity. I'm assuming we're talking about instantaneous velocity here. So what this means is I'm going to take t equals 1 and plug that into the velocity function that I found earlier. So let's see, v of 1, or f prime of 1, just depending on your preferred notation. 18 minus 6 times 1 would be 18 minus 6 would be 12. And do I have a unit here? I don't. Let's say that this is in meters per second, just to choose a unit. So this would be 12 meters per second. That's a positive velocity. That makes sense because we said at 1 second, 1 falls between 0 and 3. I'm moving to the right in the positive direction. Now I want to determine the acceleration of the object at t equals 1, which means I need to find the acceleration function. So if I want to find the acceleration function, that's the derivative of velocity, or the second derivative of position. So in this case, derivative of 18 minus 16, I'm looking up here. I know I'm kind of jumping around, but I'm looking at the derivative of this guy right here. That would just be -6. So when it comes time to evaluate my acceleration when t equals 1, well, a of 1 is just equal to -6. And now I have to give a unit for my acceleration. The acceleration determines, or it describes, the rate of change of velocity, which units for velocity are meters per second. And I want to talk about how that's changing with respect to time, so that's per second. So you can say meters per second, or oftentimes instead we'll say meters per second squared. So every second, if I think about what this means here, and actually I think writing it as meters per second is a little bit easier to look at. Look at this part. This is saying what's happening. Negative. So okay, it's negative. That means my velocity is negative. Or excuse me, my acceleration is negative. So my velocity is decreasing because my acceleration is negative. I'm losing velocity. My velocity is going down by 6 meters per second every second. And that makes sense if we look at the graph of velocity here. The graph of velocity had a negative slope. It looked like my velocity was constantly decreasing. So if it's constantly decreasing, the derivative of velocity should be negative. And we just saw that right here it is. So okay, we found velocity, we found acceleration. Part D says determine the acceleration of the object when the velocity is 0. So we actually found where the velocity is equal to 0. The velocity was 0, so v equals 0. That was 18 minus 6t equals 0. We solved that equation up here. That was this guy. So we can just jump straight to at t equals 3. If I want to determine the acceleration at that point, it's kind of silly because our acceleration is a constant function, but if we wanted to determine our acceleration at time equals 3, I would plug that into my acceleration function, which is right here, -6. So that would just be -6. Oops. Just realized I erased my negative sign earlier. So -6, and then what are my units here? Meters per second. So there's my acceleration when the velocity is 0. Last question for this particular example is a little bit tricky. It says, on what intervals is the speed increasing? This one's a little bit tricky. So let's go back up and let's look at our graph. I think that's going to be the best way to look at this. So this blue parabola, remember we said that was position, so I don't want to use S, maybe that might be confusing. Let's talk about this as position. I want to use speed, and let's decide on a color for that. Why don't we do like a brown for speed here? Speed, we said the big difference between speed and velocity, we said that, hey, if you want to look at speed, it's just the absolute value of velocity. Actually, let's do this in black. I think it'll just show up a little bit better. Speed is the absolute value of velocity, so it means it can't be negative. So we're going to identify where the velocity is negative, which is this region right here. And what's going to happen is when we talk specifically about speed, it's going to be the same as velocity right here, but when it becomes negative, it's just going to bounce across the x-axis. It reflects across the x-axis for that particular section. And what I want to do with this graph, so this black line that I've drawn in, this is speed. What I want to do for this graph is I want to kind of imagine what's happening over time. So what's happening to my speed right here? It starts off at 18 meters per second. What's happening? Well, it's getting closer and closer to zero right here. So it's getting closer and closer to zero. If I start off at a positive speed and I work my way towards zero, that object isn't speeding up. That object is slowing down if your speed starts off positive and gets closer to zero. But then what happens after that? After that, I start off at zero and my speed is going up and up and up. My speed is increasing. My speed is increasing. And I just said that out loud. I kind of answered my own question. I said, the speed is increasing. The speed is increasing on that. Oops. Let me erase just that. I just want to erase that little highlighted part just so that I don't get lost in it. Oh my goodness. That's a little bit better. The speed is increasing right here. So starting at 3 seconds, working our way towards 8 seconds, our speed is increasing. So our speed is increasing from 3 to 8. Again, not including 3, using parentheses around 3 because we said the object was stationary. It can't be gaining speed and stationary at the same time. And then all the way to 8, including 8 because we are going to have a positive speed there. So there our speed is increasing. This is sort of an idea that you may see in Calculus 2 if you plan on taking that course. In Calculus 2, we talk about parametric curves, which are sort of curves with direction. And that's sort of what I was trying to think about here, is I view time as going positive, so if I view this graph as moving from left to right, well, in this section right here, we said, hey, the velocity is getting, or the speed, excuse me, is getting closer and closer to zero. So my object is actually slowing down. That's not what I want. But then if we rebound, if we continue on with this graph, keep tracing this black line, well, after that, my speed is going up. In other words, my speed is increasing, which is exactly what I was looking for. So this hopefully better illustrates the relationship between position, velocity, acceleration, and speed. We're going to look at a few more examples after this, but I would highly encourage you to go and try some practice problems that look similar to this one so that we can hopefully gain a better understanding of this relationship between position, velocity, speed, and acceleration.